All right, high school physics. Today we're going to talk about ground-to-ground projectiles. Think of a football being kicked, like on a kickoff or a punt, where the ball goes up in the air. It's at an angle, and what we're going to do is we're going to treat that like a projectile, or a cannon being shot. That's another good example of a ground-to-ground projectile. We're going to assume that the ground is level, and so where it lands is exactly the same height or level on the other end. And so let me kind of take you through really big picture of what's going on here. This is what we're going to have to deal with. Remember, we dealt with breaking things into components. And so a projectile launched from the ground, we will have to resolve it. When we say resolve it, we mean we're going to have to figure out what is the X component and the Y component of the velocity. Most of these problems are going to be pretty straightforward of, the object is in the air at an angle of blank, at a velocity of, and so if you look at this diagram here, it's really the black line, that resultant of the right triangle, that velocity you're going to know, and then the angle you're also going to know. And we're going to have to break things into components so that we can treat the horizontal and the vertical separately. Okay, so this is a little different than our horizontal projectiles, where we knew the horizontal projectile was just firing or going horizontally, and therefore we thought of it as an object falling. This actually goes up and down in the vertical direction, so we're going to have to treat that accordingly. All right, so I'm going to switch to really the handout that I hopefully sent you home with, and I'm going to have you work this problem with me. And so go ahead and get this out, get this ready, and I'm going to kind of go through how to set up this problem and show you how this works. All right, first thing is it says a projectile is launched at 30 meters per second at an angle of 30.0 degrees. Okay, so first thing we're going to do is we're going to draw a picture of the projectile path. And all I want you to kind of catch here is that if this is kind of fired at an angle, we're going to say at 30 degrees, right? What does the path of our projectile look like? Well, it's going to be kind of fired like this. It's going to go to a certain height and it's going to come back down. It's a parabola, right? Remember what with the horizontal, we were firing and then it was falling down like this. This goes up and down. So a couple of things that we're going to deal with. And so that is really just your picture there. The information we're really interested in, you don't have to draw this on there, but we're going to find this distance here. This is our horizontal distance. That is our projectile range. Another piece of information we usually like to find is we want to know how high does the projectile go from the ground to its highest point. We usually call that delta Y. So from right here to right there, that highest point, we're going to figure out how high the projectile goes. And then the other big thing that we try to find is how much time is that projectile in the air. So those are really typically our three pieces of information that we're going to try to find in these problems. Okay, the first thing we're going to do here, it says resolve the velocity into its X and Y components. Here's what we mean. We're going to draw a right triangle. You have a horizontal velocity. You also have a vertical velocity, so that the overall velocity, that's this here. So what we're going to do here is we're going to label everything. Our overall velocity, we know this is launched at 30.0 meters per second. We also know that the angle is 30 degrees. What we are going to try to find is the X part of that velocity, the X component, and the Y component. This is just a right triangle. Okay, so let's deal with X first. Okay, this goes back to trig functions. We want to find the X component. Hey, that is adjacent to that angle. That's right next to the angle. So we're going to have to use our cosine function. So go back to cosine of theta is equal to the adjacent side, which is Vx, over the hypotenuse, which is V. We're going to rearrange this and we're going to say that Vx is actually equal to V cosine of theta. And then we're just going to plug in numbers and we're going to see what the horizontal velocity is. 30.0 is our hypotenuse, and we're going to do cosine of 30 degrees. When you plug this into a calculator, you should get 26.0 meters per second. So what does that mean? That means from the perspective of just the horizontal velocity, this object is traveling at 26 meters per second straight to the right. But we also have a vertical part of the velocity. We have to find that. So same idea, the y component is opposite of the angle. So we're going to use sine of theta is equal to Vy over V. If we rearrange that, you get Vy is equal to V sine of theta. And let's plug in our numbers. 30.0 times sine of 30.0 degrees. And then we get Vy, if we punch this into a calculator, ends up being 15.0 meters per second. This is positive because it starts with an upward 15 meters per second velocity. Okay. The next thing we're going to do is we're going to figure out how much total time it's in the air. So remember, it's going to go up and then it's going to go down. Okay. So if you look at my projectile path from part A, the first half of it is the up, and then the second half of it is the down. So what we need to do is, just like we dealt with free fall before, we either work with up or down. I'm going to work with the up, and we're going to do kinematics again. We know that the initial velocity in the y direction is 15 meters per second. I probably should put my 0 on there, 15.0 to keep 3 sig figs. When it reaches its highest point up here, the final y velocity would be 0 meters per second. Acceleration the whole time in the y direction is 9.80 meters per second squared. What we are trying to find is time. We do not know the height at this point. Okay, so what we're going to do here is we're going to basically find a kinematics equation. And if you go back to our kinematics equation, final velocity is equal to at plus the initial velocity. We can solve for t. So I'm going to rearrange this equation. I'm going to move my v sub 0 over to the left side. So vf minus v sub 0. And then I'm going to divide both sides by a. And that's going to get t by itself. So my final velocity is 0. My initial velocity was 15.0. My acceleration is negative 9.80. When I punch all of that into a calculator, I'm going to get 1.53 seconds. But be careful. This is the time it takes to go up. Or you can say it's the time it takes to go down. What I need to do is double this so that I get the total amount of time in the air, which is 3.06 seconds. So it takes 1.53 seconds to go up, and it takes 1.53 seconds to go down. Okay. That is the kind of first part of this problem. We've got to figure out how much time it's in the air. Okay, then I'm going to go ahead and clear this, and we're going to move on to, I'm going to scroll down and kind of move to the second part or second section of this problem. We're going to go to horizontal range. And what I mean by that is we want to know distance-wise from where it starts to where it ends. We want to know that horizontal range of the projectile, right? From here to there. We want to know how far it goes. Well, here's something that you need to catch, is that when it's traveling in the horizontal, there is no acceleration. It's constant velocity. So we have constant velocity in the x direction. So we know that Vx, the entire time it's traveling horizontally, would be 26.0 meters per second. The other thing we know is that the time it's traveling in the air is 3.06 seconds from the problem above. So we go back to what is velocity. Velocity by definition is delta x over t, right? So this is in our horizontal direction. This is our constant velocity equation that we can use. So delta x, which is our horizontal range, is equal to our horizontal velocity times time. That's all we're going to do. Multiply 26.0 meters per second for 3.06 seconds. And what's that going to give us? That's going to give us a distance or horizontal displacement of 79.6 meters. That's how far it travels horizontally. Okay. What is the maximum height of projectile? We're trying to find, for this path that it travels, We want to know from here to here, what is this maximum height? That's what we're trying to find. So how do we do that? Well, again, you can use the up or the down. I'm going to use the up again. You know, the initial velocity in the y direction is positive 15.0 meters per second. You know, the final velocity to get to the highest point is 0 meters per second. The time it takes, we do know that now. We already calculated that 1.53 seconds is how long it takes to get to the top position. We also know acceleration is negative 9.0 meters per second squared. What we don't know is this delta y. Now, if we go to our kinematics equation, there's more than one equation we can use, but I tend to like this equation right here. And again, I'm using delta y instead of delta x. Delta y is equal to v sub 0 y, the initial velocity of y, times t, plus 1/2 a t squared. Now be careful here, because we do have an initial velocity this time. Our initial velocity is 15.0. How long is it going up? 1.53 seconds. And then we put in our 1/2, careful here, negative 9.80. And then again, remember our time is the time it takes to go up. So we put 1.53 and we're going to square that. This term right here is positive. This whole term right here is negative. So the first part of this term would tell us if it was traveling at a constant velocity, it would tell us the displacement. But remember, it's slowing down as it goes up. So we have to have a part of this equation that accounts for the slowing down. That's where the second part is helping us. If you punch all this into a calculator, you get 11.5 meters high. That's how high it goes. Those are typically the questions that you're going to be asked. Now, there's another question that sometimes that we ask that I want to kind of add to this is at this highest point that it reaches right here, I'm going to put a red dot. At that highest point, we call this the apex, okay? At the highest point, there's a couple questions that sometimes we ask. First of all, what is the horizontal velocity at the apex? Horizontal velocity would be the same the entire time. So our horizontal velocity would still be 26 meters per second. What is our y velocity at the apex? Well, remember, this is an object that's going up and then coming back down. At its highest point, the y velocity is 0 meters per second. What about acceleration at the highest point? The entire time in the y direction, you have this 9.80 meters per second squared as the acceleration. So the only velocity it still has at that highest point is all horizontal. It has no vertical velocity at the apex, but it still has the acceleration in the negative direction for the up and down, okay? Those are the questions we typically ask. It's pretty straightforward. I think this is enough that you should be able to do the handout